In these slides, we will present a special limit of the binomial distribution called the Poisson limit. As we will understand by drawing the pie charts on the left, this limit is sometimes regarded as the limit of rare events. We will analyze this limit using the mathematical equations at the top and visualize examples of probability distributions as illustrated to the right. To become acquainted with the Poisson limit, we will concretely illustrate three situations that are parts of a limiting process. In the first situation, we consider a Bernoulli trial, meaning tossing a coin once. This is a trick coin. It is unfair. P equals 1, meaning that there is only one outcome, heads, and so the expectation of the number of heads per toss is 1. In the second situation, we consider a pair of Bernoulli trials, meaning that the number of coin tosses n equals 2. The average total number of heads x from n equals 2 tosses can be arranged to be equal to the expected number of heads from an individual toss above if we make the coin fair so that p equals 1/2. We get a variety of outcomes. Sometimes we obtain 2 heads in a row. Sometimes we get 2 tails. Often we get 1 head and 1 tail. We say often because there are 2 ways to obtain this outcome, either by getting heads followed by tails or instead by getting tails followed by heads. Finally, in the third situation, we consider tossing a coin 4 times in a row. The average number of heads obtained from a coin tossed 4 tosses at a time can be arranged to be equal to the number of heads expected per experiment illustrated in the above 2 examples. Namely, the average of x can be set equal to 1. This is done by using a trick coin that lands only 1/4 of the time on heads, meaning that p equals 1/4. We will occasionally obtain 4 heads in a row. We will many times obtain 4 tails in a row, and outcomes with 1 head and 3 tails will also be prevalent. Abstract from these 3 situations a process in which we allow n to increase without bound. In these examples, we hold constant the expected total number of heads, the average of x, obtained from experiments, each of which consists of n tosses. In order to hold the average of x constant, despite boundless increases in n, we allow p to decrease arbitrarily toward 0 in a compensatory fashion. This limiting process is sometimes referred to as the law of rare events. This does not mean that the total number of heads decreases. In fact, the total number of heads expected remains the same for each row of pie charts illustrated. However, the slice of each individual pie corresponding to the outcome heads shrinks to a tiny sliver as the number of pies per row increases. The likelihood of obtaining heads on any individual toss decreases as we move down the page, and this is the sense in which the Poisson limit is regarded as the limit of rare events. As we have already written, the average total number of heads is the product of the number of coin tosses n multiplied against the probability p for obtaining heads on an individual toss. We will now calculate the variance in the total number of heads. Because we are investigating a series of coin tosses or Bernoulli trials, we are actually studying a binomial distribution. As we showed in the previous video, the variance of a binomial distribution is n times p times 1 minus p. Substitute the ratio that specifies p above, that is to say the expectation of x divided by the number of tosses n, into the expression for the variance in 2 places. Cancel these copies of n and recognize that the n in the denominator within the parentheses grows arbitrarily large compared to the constant expectation of x, meaning that the quantity in the parentheses becomes arbitrarily close to unity. The variance equals the mean. This is one of the signatures of the Poisson limit. The variance equals the mean. To describe the Poisson limit in greater detail, we will now derive its probability distribution. Because under the hood we are considering a series of repeated coin tosses, we embark by writing down the exact expression for the binomial distribution. Explicitly substitute into this distribution the ratio that specifies p. Replace the probabilities with the average of x divided by n. The quantity 1 minus mu sub x divided by n is taken to the power n minus x. Break this power up to obtain a factor taken to the power n and another factor taken to the power minus x. In the parentheses to the right, n in the denominator grows arbitrarily large, while the average value mu sub x in the numerator remains constant. The quantity in these parentheses thus approximates 1. For these parentheses, n increases without bound both in a denominator and in the exponent while mu sub x remains constant, so we have e to the minus mu sub x. We consolidate these factors alongside the combinatoric factor, which we will now simplify. Expand the factorial in the numerator by writing n factorial as n times n minus 1 times n minus 2 and so on, down to n minus x plus 1, times those subsequent factors collectively referred to as n minus x factorial. Cancel factors of n minus x factorial upstairs and downstairs. Place the simplified combinatoric factor back into the main expression for the probability distribution. Because n is becoming very large, the factors of n, n minus 1, n minus 2, and so on down to and including n minus x plus 1 upstairs are each becoming close to n. Together, these factors are x copies of roughly n. We also have x copies of n downstairs, so we can cancel n to the x upstairs and downstairs to obtain p of x equals mu sub x to the x divided by x factorial times e to the minus mu sub x. This is the Poisson distribution. P of x equals mu to the x over x factorial times e to the minus mu. The Poisson distribution is parametrized by the average total number of heads, mu, expected from many tosses. Particular values of n, which is increasing without bound, do not appear explicitly. When the average mu is 1, the probability distribution is highly asymmetric. Out of a series of tosses, we often get 0 or 1 total heads. Sometimes we get 3 heads, and we even see some representation of instances in which we obtain 4 or 5 heads. When the average total number of heads mu equals 4, the probability distribution pulls toward the right and takes on a more symmetric appearance. And if the average total number of heads mu equals 10, the distribution pulls even farther to the right. In this video, we introduce the Poisson limit by illustrating the pie charts to the left. Because the slices corresponding to the outcome, heads, shrink to tiny slivers going from the top to the bottom of the page, the Poisson limit is sometimes called the limit of rare events. To analyze this limit, we worked through the mathematical expressions at the top and plotted the probability distributions to the right.